Okay, anybody else turning in the assignment from last time? It's going to be the last call here. Okay. All right. So I want to pick up where we left off. We're trying to find the assignment that I asked you to do at home. What's wrong, Luke? These guys, y'all aren't friends anymore? Okay. All right, that's okay. I asked you to find the parametric equation, the vector equation of the surface, this front face up here that has a tilt to it. So let me remind you of what we did last time. And specifically, when we found the parametric equations for the surface, the bottom of this thing, right? What we did is we said, okay, if you look at that bottom piece just in the xy plane, we know that since it's on the ground, the z component of our vector function will be 0, right? That'll keep it flat. And then this looked a lot like a type 1 region back from double integrals, with the exception that we're going to switch x to u and switch y to v. And then notice that if we let x vary, right, between 0 and 3, if we pick some arbitrary, u, if we let u vary between 0 and 3, then we want our v to actually be everything in here, right? So it would draw that entire line segment. And to do that, what we did was we let v in the equation just be v, and we restricted it between 0 and the line in order to let v go up and down, right? And that created the sheet that we needed. Well, the only difference between this and this plane that comes in at an angle is that, like, if you looked at it straight from the top, right, it would look exactly the same, wouldn't it? The only difference is the z is different. Now, I thought this might be a good time to remind you, back when we were doing triple integrals, our regions of integration were three-dimensional, right? Solids. If you were to define this tetrahedron as a triple integral, you would say my x's are between 0 and 3, right? My y's are between 0 and this line, right here. And then my z's are between 0 and, which is the ground, and what? The plane equation, right? Solve for z, that's what this is. But that would make the solid, wouldn't it? Because your z is everything in between 0 and that plane. What we want for our vector function is to not have every z between this plane and down to the ground. We just want the one on the plane, right? So the only difference is that this right here needs to live on the plane. And so what you had to do at home, I'm going to have some trouble talking today. I'm getting over something, allergies. My throat's real itchy. You had to find the plane equation, so that's where you took two vectors on there and crossed them and got your normal. Okay. So the plane equation, what I got was this, 8x plus 6y plus 12z equals 24. I believe that's what I got, and you can reduce that out. And if you solve that for z, should I just reduce everything by a factor of 3 right now, or a factor of 2? You get 4x plus 3y plus 4z equals, what's that, 8? And then you solve for z. What's what? Yeah, sorry. Sorry. I don't know what I'm doing. And then solve that for z, right? Okay. Man, maybe I should start this whole day over. That's how I felt. This is how I felt all day. The way what I'm doing up here. All right. So here I'm going to solve this for z, and replace x and y with u and v, right? So I got. I left it as like this: 12 minus 4u minus 3v over 6. And of course, you could split that up and do 12 over 6 is 2, and then fractions. So what's really important for you to understand here is that this is only going to give you a single value for the z. Once you pick your u, right, your v's are stuck between two numbers now. And everything in between those two numbers is going to get plugged in here. And so what's going to happen, I'm trying to draw it for you. You pick a u, which is like the x. You pick a u, then it draws, your v's are restricted between here and here, aren't they? That would be like this line was. And then everything on that line gets plugged into this, which would give you something like, just those points up into the plane would give you that line segment on the plane. And if you do that for every u value, right, pick another u, every point here up into the plane, then eventually you draw the whole plane. Understand? Okay. We're going to move on. We're going to finish up this worksheet. So hopefully anyone need one? I think I have an extra. You have like $2 or something? Yeah? Okay. Did anybody try and do the other ones? No? All right, so here it is. You have part of a cylinder, all right? And it's hard to tell from the picture, so I'll turn it to the side. Can you all tell what the restrictions are here on our y coordinate? I think it's 1. I think it's a 1 to 4. See that? 1 to 4? Okay. And then can you tell what the radius of this cylinder is? Can you all tell? 1. Can you all tell? All right. So we need to come up with the parametric equation, the vector formula that would draw that surface. So any ideas? I need it to be r of uv, right? I need 3 components. Okay, so you have a bunch of circles, don't you? And so you could just start by trying to draw just one circle, like this outer edge. If I try and draw that outer edge, that is a circle in which plane? Parallel to which plane? The xz plane, right? Understand? So how we would draw a circle in the xz plane, and it's a unit circle, is to use the whole r cosine theta, r sine theta thing, with r being fixed here at 1. Yes? But instead of using theta, I need to use u or v, so it's your choice. There's no like accepted convention that we always use or anything like that. So what do you want? U or v? U? Okay, so in the x component, I'm going to put cosine u. In the z component, sine u. Everyone agrees that draws a unit circle that would be parallel to the xz plane. Yeah? Then I just need to take that and move that circle back and forth, changing the y coordinate between where? 1 and 4, right? So like if I just put 1 here, that would draw me this back edge, wouldn't it? If I put a 4 here, it would draw me this front edge. But I want everything in between. So if I'm going to need that to vary, I'm going to have to put a variable here, right? But I can't use u, so I'm going to use v. And then I'll let my u go between 0 and 2 pi. That'll draw me circles. I'll let my v go between 1 and 4, and that will move those circles back and forth, and that'll give me the cylinder. That's not so bad, right? Questions? What is the difference between that and this equation? My parametric equation that I just gave you and this, what's the difference? That goes forever in each direction, right? And there's no easy way for you to tell me how to control this, right, if I want that, unless you actually explicitly say, you know, y is between 1 and 4. Then they would draw the same thing, wouldn't they? Just want you to understand that this equation right here is not the same as what we just came up with. This is actually more than what we wanted. Okay, now this one. Find the vector function r of uv which yields the red end cap of the cylinder shown here. So it's the same cylinder we just drew, okay? But I want this red end cap instead of the blue. So what's the difference here? Not the back, just the front. I just want this front piece. What? Two. Yeah, see, look, when we drew the cylinder, it was the same circle the whole time, right? Right? And it just moved it back and forth between 1 and 4. Here, we don't want the same circle. We want a bunch of circles from radius 1 all the way down to a point, and we don't want to move it back and forth, which is good because we needed a variable to move it back and forth, didn't we? So I think it should look very similar to what we just had in terms of the fact that we can use cosine in sine. That draws circles. But this time we'll have a varying radius. So how about we use cosine u, sine u again. That will draw me circles in the xz plane. But I don't want unit circles, right? Something you can control. So how about we use that other variable v here? V times this. V times this. Now what about the y? That's going to have to be 4. If I'm going to be this front end cap, right? That's going to be 4. What if I wanted the back end cap? It would just be a 1, right? What if I wanted to draw the whole solid? Well, I can't use these, okay? These only draw surfaces. Now, you could introduce a third variable, but we're not going to. You could, though, and that would solve the problem somewhat. All right, so this is it. What are my restrictions on u? 0 to pi. And v, I want these represent the radius, right, or the radii of the circles. I want them to go all the way down to a single point, 0, all the way out to 1. Any questions? Sure? Everyone understand the fundamental difference between those two problems? All right. Let's look at the next one. All right, I tried to give you as much information as I could on this one, on your picture, but let's look at it from the side. It touches the xz plane. You see that? Yeah, can you all see that? Touches the xz plane. And this cylinder, if we look at it from this side like this, the cylinder has a radius of what? 1 again. And then it gets sliced. So what did I write on yours? Hold on. I put y equals 0 on the back side, like this. Y equals 0. I put, what? Z equals what? And then anything else? And then the cylinder is the same as the one before, right? So you could, if we wanted to, label this one x squared plus z squared equals 1, right? Understand? So what we want in this problem is to find the vector function which yields the three surfaces shown. That means we're going to have to come up with three different vector functions. We can't draw them all at the same time. We have to just do one at a time. All right? So let's label these. Why don't we call this one over here the backside? Okay, why don't we call that backside S1? Why don't we call this one over here S2? And the one that comes from here S3. Does everyone understand that this is a cylinder that's been cut with the plane y equals 0 at the back, like this, cutting it at the back, and then cutting it with the plane at an angle that cuts it off this way. And that's the plane that we use to cut it at this angle. Got it? So we have three surfaces. Let's start with S1 because it's probably the easiest one. All right, S1 looks exactly like the one we just did. I'm going to call this R sub 1, so everyone knows which one I'm talking about, of uv. And this should be v cosine u, 0 v sine u, and u's between 0 and 2 pi, v's between 0 and 1, right? That should draw me the backside. Now is the question of which one do you want to go after next. S2 seems natural because that's the way I labeled it, but I think S3 is easier to see. Okay, on easiness, yes. So what is the difference? What's the only difference? That's a hint. What's the only difference between S1 and S3? If you looked at them from the end, if you were standing here on the y-axis way down there, and you were to look at them, could you tell any difference between S1 and S3? No, I'm never going to get this back where I want it. Oh, damn. Okay, I guess I am. Okay. They look exactly the same, right? Because the only difference between them is the y-coordinate, right? You can't tell that it's coming out, like this one is actually coming out at you, where that one's laying flat. So the only difference between S1 and S3 is this y value. You still have to draw everything. This is like a disk, right? Almost. It's not a disk, but you still have to draw everything on the inside of it. Okay? But what can you tell me about that y, the y value on that S3? It has to follow this equation, doesn't it? Because it has to live on the plane. Understand? So since I know this is the only difference, I come in here and I look at this equation and I solve it for y. Because that's the part I'm interested in. Solve this equation for y, and what would you get? Y is equal to z minus x plus 2, right? So let me write this down. S sub 3 is R sub 3 of uv. And this should be equal to, I know that my x component must be this. My z component must be this. Right? That's still giving me that disk effect, right? The y part, the part that's coming out at me, though, is going to change depending on my x and on my z. And it will be exactly my z coordinate minus my x coordinate plus 2. But what's my z coordinate? V sine u. Minus what's my x coordinate? V cosine u plus 2. So right in here, I'm going to need a little more space. This should be V cosine u. That's the x. The y is z V sine u minus x V cosine u plus 2. And then V sine u. Do you all see that? To determine my y coordinate, right, I have to refer back to my x and to my z to get my y. So this is the x, this is the z.